What if there were a code embedded in numbers like 1, 2, 3, 4? What if there was a secret code embedded in them? And as a matter of fact, there is a secret code built into numbers, and it is mind-blowing. And so we're going to talk about a particular set that's called the Mandelbrot set. This was discovered in the late 1970s, early 1980s, named after the person who really discovered this, Benoit Mandelbrot. It's the set of all numbers, C. C is a number that is potentially part of the Mandelbrot set, for which this other number, Z, remains small according to this little formula. And if that sequence of Z stays small, then the other number, C, is part of the Mandelbrot set. On the other hand, if the sequence of Z gets very big, if it goes 1, 2, 100, 1,000,000, 1,000,000,000, then C is not part of the Mandelbrot set. And we'll do a couple of examples to let this sink in. It's pretty straightforward, really. So we're going to ask, is the number 1 part of the Mandelbrot set? So C equals 1, okay? And we're going to plug that into our formula then. So we have Z squared plus 1, because that's the number we're testing. That becomes the new value of Z. Now, the first value of Z is 0 by definition. So that's the first value. So we plug that in, and we have 0 squared, which is 0, plus 1 is 1. Yeah, 0 squared plus 1 is 1. So that's the next value of Z, okay? And what we'll do is we'll put that 1 back into the formula. That's the new value of Z. So now we have 1 squared, which is 1, plus 1 is 2, okay? And you plug that back in, so we have 2 squared is 4. 2 times 2 is 4, plus 1 is 5. Okay, you're getting this. You put it back in. 5 squared, 25, plus 1 is 26. Okay, we put that back in. 26 squared is a big number. And you put that back in. Okay, now you see what's happening here? Is the sequence of Z staying small? No. So is the number 1 part of the Mandelbrot set? No. Because it has to stay small for it to belong. There's one more complication, and then we get to the really cool stuff. The other complication is that the Mandelbrot set also includes what are called complex and imaginary numbers. Okay, so an imaginary number is a number that when you square it, you get a negative number. And that's a little hard for us to understand, and so they call them imaginary. Positive number squared is positive. And yet, the imaginary number times itself is negative. Imaginary numbers are not negative because a negative number squared is also positive. And imaginary numbers are not 0 because 0 squared is 0. Weird. So we have a number that's not positive, it's not negative, and it's not 0. So if you consider a number line, so here we have a number line. Now the positive numbers are to the right of 0 along that number line. The negative numbers are to the left of 0 along that number line. So how do we represent a number that's not positive, not negative, and not 0? Well, you put it up above the number line like that. It's not on the number line. It's on a different axis. And by multiplying I by the other real numbers, you can have all kinds of imaginary numbers. You can also have numbers that are called complex, and they're off axis. They're called complex because they have a real part and an imaginary part. So the Mandelbrot set also includes these imaginary and complex numbers. I'm trying to figure out if there's a pattern to the numbers that belong to the Mandelbrot set. And it turns out there is. And so we'll take the points that belong to the Mandelbrot set, and we'll color those black. And you have the computer check more points, and you find that all those points right there belong to the Mandelbrot set. When you run it through that formula, Z stays small. And then the points that do not belong, we'll color those red. And had we checked these other points, we would find that they do not belong. And so you see, as you plot more and more of these points, a pattern starts to emerge. What's it going to look like? Well, you have the computer run through thousands and thousands of points. You have the computer check each one of those numbers, and a pattern emerges, and the pattern looks like this. The shape is remarkably interesting and unexpected. The main shape that looks kind of like a heart, that's called a cardioid. And a cardioid is what happens when you take a circle and you take your pencil on it and roll it around another circle of equal size. The shape you'll get is a cardioid. And you can see that, sure enough, the main part of the Mandelbrot set is a perfect cardioid. All the other shapes that are growing off of it are circles. All these perfect circles. You notice that that top circle there, it's got a circle on top of it, another one on top of it on smaller and smaller scales, and it goes out and forms this little tree, and it's got 3 stems to it, including the trunk. So it's got a trunk and 2 stems for a total of 3 branches. You see that there? Now the next one to the left branches into 5. Can you see that? I mean, it's kind of small, but you can see the 5 branches there. The next one is 7, 9, 11, 13, 15. It's all the odd numbers. And by the way, they don't stop. They go to infinity. And then on the other side, you have the odds and the evens. You have all the numbers there in terms of the number of branches. And of course, you can take 2 of those numbers, like 5 and 3. Now, 5 plus 3 is 8, okay? And it turns out that the bud in between those 2 has 8 tendrils. Interesting. And that's true of all of them, both on the left side and the right. And then on the left side over there, you got this kind of spike that goes out. And you see there's this little bump on the end of the spike. So let's take a look and see what that looks like. So we'll zoom in on it. And that little bump, turns out, it looks like the entire Mandelbrot set. It's a mini Mandelbrot set. And, oh, it has a little spike growing off of it, too, with a little bump. What could that be? Well, let's zoom in on that. And, oh, interesting. Absolutely fat, and it's got extra spikes growing off of it. And that's got a little bud. How about that? Now, of course, you could do that literally forever. And take a look at how small this is compared to the original when we zoom back out here. Look at how tiny it is. Isn't that remarkable? God's understanding is infinite. Numbers are an aspect of God's mind. God is responsible for numbers. And so it makes sense in the Christian worldview that when we explore and study numbers, we find intelligence in them. We find evidence of patterns. And not only intelligence, but infinite intelligence, because this thing repeats infinitely. A structure that repeats itself on smaller and smaller scales is called a fractal. So the Mandelbrot set is one example of a fractal. There are other types of fractals. There are other sections of the Mandelbrot set that are fractal. We could zoom in, for example, on one of these little tendril features here and zoom in on that. And you'd say, well, that's interesting. You think what's going to stop at some point, right? Eventually it'll even out and you'll get, but it just keeps going. It's infinitely wiggly, you see. It's wiggling around like that, and you zoom in on it, and it keeps going and keeps going and keeps going. It's just mesmerizing to watch this thing and see the scale here. And it gives you a little taste of what God's mind is like, to be able to think infinitely. And we can zoom in, for example, on this cusp between the main cardioid and the disc. And we find they call it the Valley of the Seahorses, because you see over on the right side, it looks like seahorses. They're upside down, and we'll change them every now and then just to keep things interesting. But just keep in mind, black always represents numbers that do belong to the Mandelbrot set, and then colors represent those that do not belong to the Mandelbrot set. And bright colors are very close to being on the Mandelbrot set, but not quite a part of it. So let's zoom in on one of these seahorse structures over here. You see it looks like an upside-down seahorse. Isn't that fascinating? And quite beautiful. Well, let's zoom in and find out what this seahorse is made of. It's the central hub there looks kind of like a spiderweb type structure, right? And I've found from experience you can zoom in on the center of that till your heart's content, and it doesn't really change very much. It goes on infinitely. And so I thought, well, okay, let's go off to the side and figure out what the strands of the spiderweb are made of. So let's go off to the side here, and we find that the strands are made of more spiderwebs. And we zoom in a little bit more, and you find that there's sort of 2 hubs there. You see the bright yellow hubs. And then in the middle, it goes from 2 to 4. And as we zoom in, it'll go from 4 to 8 to 16, 32, 64. It doubles each time. And as we zoom in on that central hub, we find, oh, isn't that interesting? You see it going from 4 to 8 to 16 and so on. And in the middle, of course, you have another baby Mandelbrot set. And again, look at how small this is compared to the overall shape as we zoom back out. It's just a tiny little infinitesimal, and we could have zoomed in on any one of those strands. I just picked one at random. Let's go back to that valley. Now, the Valley of Seahorses is on the right. On the left, we find the Valley of the Double Spirals. And I'll zoom in on one of those now. This is my favorite part of the Mandelbrot set. I think they're very beautiful. They remind me of spiral galaxies, actually, which is an astronomer I really appreciate. God apparently likes spirals because he's built a lot of them into nature, and he's built them into math, which is remarkable. Who would have guessed that there would be a spiral, a beautiful spiral, built into that little formula, z squared plus c, or rather built into numbers when we run them through that formula. And let's zoom in on that a little bit. And again, I found you can zoom in on the center forever, so we'll zoom in on the side. and you find the spiderweb type structures, you find more double spirals, and you find a new structure. I call them bow ties. They're kind of in the middle. You see it looks like kind of like a little bow tie, right? And it's got two double spirals. So we'll zoom in on one of these bow ties, and we find that it's, again, you have the two double spirals as we zoom in on the center there. And in the middle, you find another mini Mandelbrot set. You're not surprised this time, but we serve a God who is beautiful, who makes beautiful things. And when we examine the way God thinks about numbers, which is what mathematics really is, we find it's immensely beautiful.